In this video, we are going to talk about divergence and curl. This is our overview slide, which we'll spend about 5 minutes going over before we talk about these other topics of divergence, the physical meaning and picture for divergence, curl, the physical meaning and picture of curl, and finally this last theorem, which is not in your book, but I find very useful. We will start by defining divergence, and the divergence is the del operator. Remember the del operator here, the partial with respect to x, partial with respect to y, and partial with respect to z, acting on a vector field with the dot product producing a scalar. And here's the formal definition, but let's look at that. Let's say we have a vector field a bar. So this is our function that takes a vector x, y, z and produces a vector. This is our x coordinate, which is a function of x, y, z, our y coordinate, also a function of x, y, z, and our z coordinate, a function of x, y, z. So we're going to dot our del with our vector function. So we get d dx, d dy, d dz, dotted with a1, a2, and a3. That gives us dA1 dx plus dA2 dy plus dA3 dz. And as you can see, because it's a dot product, our result is going to be a scalar. A quick example, we'll compute the divergence of our field f is equal to x squared y, z, and x, y, z. So the divergence of f is the dot product, and I should put a little bar on top of these, the dot product of the del with f, so that's d dx, d dy, d dz, dotted with our x squared y, our z, and our x, y, z. So the partial derivative of our f1 with respect to x is just 2xy. Our partial derivative of our second coordinate with respect to y is 0, and then our partial derivative of our last coordinate with z is going to be xy. So our final dot product, when we sum this up, we get 3xy. And just comparing kind of this here, which I feel like is the easy way to introduce divergence, but comparing it to this definition here. So I move this definition down here. So the dot product of del with A is equal to the ith basis vector d dxi dotted with a sub j, e sub j. So this here, since we have the repeated index I, is a summation, and we're going to dot it, and this here is also a repeated symbol, so it's a summation. So when we sum from I equals 1 to 3, we get E1 d dx1 plus E2 d dx2 plus E3 d dx3. And then here we have our A1 function times E1 plus A2 times E2 plus A3 E3. And we dot these two. And it's funny, when I take a quick look at this, because they're summed, these look like a scalar times a scalar, but they're not scalars because this is because of the E1, E2, E3, right? So this is really d dx1, comma d dx2, and d dx3. Similarly, over here, this is really A1, A2, A3. It's funny because I paused for a minute because I thought these were scalars, but they're not. They're vectors. So we're going to dot this. So and the other step I did is I let 1, 2, and 3, x1 equal to the x coordinate, x2 equal to the y, and x3 equal to z, because that's what I'm used to seeing. So then my dot product of del dot A becomes my d dx, d dy, d dz, and over here I have A1, A2, A3, and then I get exactly what we have over here. And then putting it back into summation notation is dAI over dXI. And then for you physics majors, another example would be the charge density of a region, that's P sub rho sub C, can be calculated using this divergence relationship right here. And just as important as this definition is the physical meaning and picture of divergence. So the explanation I like is that if A is a velocity field of a gas or fluid, then the divergence of A represents the rate of expansion per unit volume of the gas or fluid, or the flux density is another way of expressing this. So if the divergence of a field is equal to 3, that means the gas is expanding 3 cubic units per unit of volume per unit of time. And if div f equals 0, we say that f is incompressible. A couple of other notes: if the divergence of a vector field is positive in a region, then the region is called a source, and field lines are born or they start in the source regions. If the divergence in a region is negative, the region is called a sink, and field lines terminate in the sink regions. And last, if the divergence of a vector field is 0 in a region, then all the field lines that enter must also leave. And here we have an example of a source and sink. So we're going to graph the vector field and calculate that divergence of f of xy equals xy and g of xy equals negative x negative y. We're going to compare or contrast the divergence of f and g. We will start with f of xy equals xy, which is a nice little vector field. I rewrote the formula here. I have different points for x and y's, and I started with small values, which is always a good thing to do. And then I wrote what f of xy equals, and it's just equal to the same vector. At the point x equals 1, y equals 0, that's this point here, I need a vector that is 1 unit length pointing in the x direction, so it looks like this. Remember, I can also think of at the point 1, 0, which is here, I take the vector 1, 0, which is this vector, and I move it to my point 1, 0. I did similar things for the next 3 vectors. So at the point x equals 0, y equals 1, that's this point here, I need a vector pointing in the positive y direction, that's 1 unit length, that's here. And then at the point x equals negative 1, 0, that's this point here, I have a unit vector pointing in the negative y direction. And then at x equals 0, y equals negative 1, that's this point here, I have a unit vector pointing in the negative y direction. I'm sorry, this was negative x direction. This one's negative y direction. And at the point 1, 1, so that's going to be this point here, I have the vector 1, 1. So I drew my vector 1, 1, and then I'm going to go ahead and move it so that it's at my point 1, 1. From here, there's a little bit of a pattern. So if I'm at this point here, x equals negative 1, y equals 1, I'm going to have that vector just translated over. So it starts at that point. Similarly, this point, and you can also, make the table yourself, but these are the points here. Now, let's say I want to do some vector that's further out, and I'm going to do a vector that's, beyond the tip of this vector, just so my graph doesn't look too cluttered. So at the point, say, x equals 3, y equals 0, so at 3, 0, my f of xy is going to be my 3, 0 vector. So it's going to be like this, length of 3. Over here, similarly over here, I'm going to have a vector at y equals 3, x equals 0 that goes up 3 units. So essentially, as we move out, we're going to get longer vectors, and then essentially the same length as how far we've moved out. From there, I guess I can do this vector. So here, I'm at the point x equals 1, y equals 2. So at this point, I need a vector that is x equals 1, y equals 2. So I'm just going to draw that this way. And I can do something similar over here. X equals 1, y equals 2. And I can add more vectors, but you can see it's a radially outward kind of vector space, and the vectors get longer as you get away from the origin. I can now calculate my divergence, so d dx d dy dotted with my xy, partial derivative with respect to x is 1, partial derivative with respect to y is 1, so 2 is my divergence. And since this is a positive divergence, it's positive, this region is a source, and field lines are born in the source. So here we would say the divergence is away from the center and it is a source. Our next vector field is g of xy equals negative x negative y. So again, I plotted some small points for xy, and then I plugged it into g of xy. I start with at my point x equals 1, 0. So x equals 1, y equals 0. That's this point here. I have a vector that points, it's a unit vector that points in the negative x direction. So unit vector pointing in the negative x direction. My next point is at 0, 1 over here, and it points, or the vector at this point is going to point in, it's a unit vector, in the negative y direction, so here. And then I added at x equals negative 1, 0, something that points in the positive x direction. Here at x equals 0, y is equal to negative 1, something that points in the positive y direction. That's this one here. At the point 1, 1, that's this point here. So at 1, 1, I need the vector negative 1, negative 1. That's this vector here. So I'm going to move my vector negative 1, negative 1 to my point 1, 1. Similarly, at the point negative 1, x equals negative 1, y equals 1, x equals negative 1, y equals 1. So that's this point here. I'm going to have the vector 1, negative 1. So x equals 1, y equals negative 1. That's this vector here. But again, I need to move that vector to the point negative 1, 1. You can see if you have the point x equals negative 1, y equals negative 1, that's this point, you're going to get the vector in the positive 1 direction, y direction. So you get this, and then you can work the same numbers out for this area here. And now to get some of the bigger numbers, let's say I have the point 2, 0, that's x equals 2, y equals 0. I'm going to have a vector that points in the negative x direction 2 units. So essentially everything, and actually this is hard to draw because it's going to go all the way through the other vector. Everything is pointing all the way back from wherever you are, whatever distance you are, you want to go all the way back to the origin. And this is the picture I'm going to keep because the one with the blue arrow starts to get cluttered. But I can now calculate the divergence of g, so d dx d dy of negative x negative y gives us negative 2. So that means we're pointing inward and we have a sink. Now we've covered divergence and we'll move on to curl. We start with the definition of curl, and that is the del operator acting on a vector field with the cross product. So here is the notational definition, and here's the picture that I like to do, the del cross A, and then I have the determinant representing the cross product. So for a quick example, let's let our vector field v of xyz equal y negative x 0. We want to find the curl of v, so that's del cross v. So here's our determinant I, j, k direction vectors d dx, d dy, d dz, and our vector field y minus x 0. So doing the cross product in the I direction, crossing these two out, and then cross multiplying, I got d dy of 0, 0 minus d dz of minus x is 0, so 0 in the I direction. For the j direction, crossing these rows out and doing the cross multiplication, d dx of 0, 0 minus the derivative with respect to z of y is also 0, so 0 in the j direction. And in the k direction, d dx of negative x is negative 1 minus d dy of y is 1, so I get a minus 2 in the k direction. So that's our quick example. And then one last example for your physics majors, this Maxwell's equation features the cross product. And then I also have an addition of a theorem that is not covered in your book, but I find it is useful because it allows you to determine if a vector field is a gradient or potential field. And that is, this theorem says the curl of any gradient or potential field is, and here's the definition of the curl, and here we're saying that if we have a vector field, f, it could be the gradient of the scalar field little f. So it could be a gradient field or potential field if the curl is equal to 0. So from our last example, we have our vector field v of x, y, z is equal to y negative x, 0. We want to show that v is not a gradient field, also known as a potential field. So by the theorem, if v is a gradient field, then the cross product of v is equal to 0. But we did this curl in our previous example, and we got the curl of 0, 0, negative 2. But since the curl is negative 2 in the k direction, v is not a gradient field. So in other words, there's no scalar function f that you can take the gradient of to get this vector field v. And just as important as the definition of curl is our physical interpretation of curl. And curl is associated with rotations. And this is my illustrations to explain the difference just between rotation and circulation. I think your book uses rotation and circulation almost the same, except rotation being micro and circulation being macro. But this is how I'm going to explain. First, a non-zero curl. If we have a paddle wheel, so this illustration is over time. This is where time starts. We have this little disc that we can mark with arrows pointing straight in the north direction and an arrow pointing in the east direction. So we have this little disc that we've marked up, and we put it in, say, some water, some sort of flow. Over time, it moves this way, and it also rotates. So this arrow now points at this 45-degree angle, and this arrow here is pointing, southeast. As it moves over time in our flow, this arrow now points straight east, and this points south, and it moves, and you can see that the disk is rotating as the whole disk circulates. So it makes a complete circle and it rotates. The rotation is what gives it non-zero curl. Contrast this with this disk in a different flow. So we put this disk in a different flow, and it still makes this circle. However, the disk itself does not rotate. The arrow that points north, it keeps pointing north. So this is where an example where even though the disk is traveling in a circle, the curl is 0. And here I have this non-zero curl. I've made an animation of this disk in this flow. So that was my very impressive animation, but I'm not going to do one for curl equals 0. You can imagine it in your head. And your book points out this common misconception. So it's a common misconception to conclude that if a vector field has a non-zero curl, then the field line should be curved, while a field with 0 curl should be straight. And these confusions come from confusing circulating vectors, or these vector fields where things are going in circles, and the idea of rotation. So as we've seen, it's possible to have a circular vector field with a curl of 0 as well as a non-zero curl. These are our two examples. Here we have a circular, something traveling in a circle, but here we have non-zero curl and here we have 0 curl. Similarly, you can have things that travel in a straight line with no curl, but you can also have something that's still rotating as it travels in a straight line. Your book has gone to length to mathematically prove the physical interpretation of divergence and curl. And because it does in fact take up a large portion of your book for this chapter on divergence and curl, I felt obligated to cover it. But I don't feel like it gives you a lot of wisdom. So if you feel like you've had enough, I'm going to say thank you for watching. If you feel you need to, or you would like to see kind of how the mathematical derivation of these physical properties are, we're going to do that next. For the physical picture of divergence, we're going to develop a continuity equation which describes the change in local particle density of a fluid as a function of time. So we're going to let rho of x, y, z of t be the number of particles per unit volume, and the velocity of x, y, z of t be the velocity of these particles at the point x, y, z at time t. And because this involves calculus, we're going to consider the differential volume at time t. So we're going to take this little tiny cube and we're going to study this little tiny volume, and we're going to consider that delta t, or delta tau, is equal to dx, dy, dz. So very small changes in x, y, and z. And it's going to be located at the point x naught, y naught, z naught. And we're going to equate the net flow of particles into or out of the volume with the corresponding change in our density, our rho. So the total number of particles in the infinitesimal volume n, represented in this volume here, is equal to rho d tau. Then the change in n over time is equal to the change in rho with respect to time in this volume, dx, dy, dz. The rate of change needs to account for the flow of particles across the 6 surfaces of this little volume cube. So we're going to start with the bottom surface. I've redrawn my very small cube over here, and I've highlighted the bottom surface and also the top surface for later. So the total number of particles that enter the volume in a time dt across the surface is equal to the number of particles in the region dx, dy, and then I substituted for dz the velocity with respect to z dt. So vz dt gives us dz, and that's that little incremental height here. So again, we want the number of particles entering this yellow portion. A positive vz adds particles while a negative vz removes them. So looking at the change in number of particles for the bottom, so I denoted bottom, dt, is equal to our rho, our density, times our dx, dy, and here is our dz, our v of z. And now just to kind of simplify our notation, since rho and v of z both depend on the same variables, x naught, y naught, z naught, t, we're going to combine these two into our current density j vector, which is equal to p times our v vector. That gives us now our change in the number of particles at the bottom, dt, is equal to j of z dx dy. Similarly, we can do something for the top for particles leaving, although I guess if they're entering them, vz is going to be negative. It's the opposite of what we did for the top. To make more room, I've kind of summarized some things here. We have our differential volume, we have our formula for number of particles, we have our cubes again, we let j equal to pv, and then we have the formula for the change in the number of particles on the bottom with respect to time, and then the change in number of particles at the top with respect to time. Oh, and there's something I need to clarify. This here, because this is the bottom, our x naught, y naught coordinate is x naught, y naught, z naught, t, but for the top, our z coordinate now changes to z naught plus our dz. So these two are not the same. And the fact that they're not the same, when we add the change in the bottom plus the change in the top, we're going to have j of x naught, y naught, z naught, t. This is the bottom because z is at z naught, minus j of x naught, y naught, z naught plus dz. So that gives us the top because we're at z naught plus dz of t, x and y. This part here is simply the change in j. So in other words, the top and bottom is negative j of z dz at x naught, y naught, z naught, dx, dy, dz. Switching gears a little bit and looking at our total flow in the differential volume, that's dn dt, is equal to the change in the x, the y, and the z direction. and looking at this form, oh, dx, dy, dz. So this is essentially the negative of the dot of the del product with our j vector. So the continuity equation then is d rho dt is equal to negative our del dot j. And this is what gives us the interpretation of if the divergence of a vector field is positive in a region, it's a source and field lines are born in source regions. And if divergence in a region is negative, the region is a sink. Next, we're going to look at developing a mathematical argument for the physical picture of curl. And we're going to start by considering a vector field V that is the function of x and y only to simplify things. The curl of this field points in the z direction. So here we have our vector field with x, y, and then 0, and then our vx, our vy, and then in the 0 vector, 0 direction, we have 0. We take the curl, and that's going to give us 0, 0, dvy dx minus dvx dy. Here we have our vector that depends only on x and y, also is 0 in the z direction, and our curl that we just calculated. And we want to consider the line integral of the vector field around this closed path C. And we're going to say that this closed path, we're going to construct it as a square, C1, C2, C3, C4. So it's the sum of these four line integrals. We will start with the first line integral C1, and the first step is to parameterize our path. So you can see what happens. In the y direction, we stay at y naught. In the x direction, we start at x naught, and then we end up at x naught plus delta x. So we're going to parameterize our path C1 with the variable t, and t is in the x position. So x goes between x naught and x naught plus delta x. Y stays at y naught, and z is at 0. So here we have our parameterization. We can take the derivative of our path now. So here we have a dx, and then y naught is constant, so it goes to 0, and we have 0. So plugging into our integral, we have our limits of integration from our parameterization, x naught to x naught plus delta x. We take the derivative of our path, so dx 0, 0, and we dot it with v composed of our path. So that's v composed of x, y naught, 0. When we do the dot product, we have our dx times our x. We have our 0 here, and then we'll have 0 here. So what we have is the integral from x naught plus delta x, dx of our vx. That is the xth component of v. We are then going to use a Taylor series approximation for v of x at x naught, y naught, and that's approximately equal to vx at x naught, y naught plus derivative of vx with respect to x, plugging in x naught, y naught, times x minus x naught. And again, x minus x naught is simply delta x. In case you've forgotten what the Taylor approximations are, they are used to approximate a function using a polynomial. So you can approximate any function using a polynomial, and how accurate that approximation is depends on what degree polynomial you have. So a third degree polynomial is going to be more accurate than a second degree polynomial, which is more accurate than a first degree polynomial, etc., unless you actually are approximating a second order polynomial with a Taylor function of second degree, then it'll be exact. Looking at this picture here, and I'm sorry I didn't draw a better picture, but this is what I've got. So here you have a function that represents this surface in black, outlined in black. You can then approximate this function at a particular point. So the idea is like the function, here, it might be different than the function over here that you use to approximate this portion of your graph, or you approximate this portion of the graph. So you choose a point and say, I'm going to approximate this portion of the graph. You can approximate it using this single point. Or like you've used to approximate curves at a single point using a tangent line, you could use a tangent plane, and that equation of the plane will approximate this curve a little bit better than just a single point. Or you can then, and a tangent plane it's of degree 1, but you can actually go to degree 2, where you have a quadratic, and then maybe this quadratic will serve as your approximation for this function at this point. So for a second order, that's second order, so a second degree polynomial, Taylor's formula for several variables is if you have a function you're trying to approximate, and it maps from Rn to R, its first and second order partial differential at point A gives us this approximation polynomial, P2. So it's a polynomial of degree 2 that we're trying to approximate this function f with. And that's going to be the function at the point AB that you're trying to approximate the function, plus the partial derivative with respect to x applied to AB times x minus a, plus the partial derivative of f with respect to y of AB times y minus b, y minus the y coordinate. Here this was x minus the x coordinate, plus, and this is where you have the second degree, 1/2 f of the second order partial derivative, f of x, ab, times x minus a squared, plus f partial derivative with respect to x and then y of ab, x minus a, y minus b, plus 1/2 partial derivative of y with respect to y, ab times y minus b squared. So again, this is the formula we have here. Here we have our Taylor series approximation for v of x evaluated at x naught, y naught, and that's approximately v of x evaluated at x naught, y naught, plus dv of x dx evaluated at x naught, y naught times x minus x naught. And remember, x minus x naught is delta x, so I have this plugged in now into our formula for our line integral. So we have our vx evaluated x naught, y naught, delta x plus 1/2 partial with respect to x dx evaluated at x naught, y naught times delta x squared. We can get a similar expression for C3 starting with our parameterization. At this point, x is going to go backwards, so it's going to go from x plus delta x to x naught. Our y value is at y naught plus delta y, and then z is equal to 0. So our expression is going to be C3 dr dot v is equal to x naught plus delta x, x naught, dx v of x. The calculations are similar, so we end up with this value here for C3, or this approximation. When you add C1 to C3, you get negative delta Vx dy evaluated at x naught, y naught, delta x, delta y. We can continue for the whole curve, so we could be adding C1, C2, C3, C4, and this is what we will get. It's approximately equal to the partial derivative of Vy with respect to x, x naught, y naught, minus partial derivative of respect to y of V of x evaluated at x naught, y naught, all times delta x, delta y. And here, using this, the curl of v, when v is only a function of x and y, is equal to 0, 0 dvy dx minus dvx dy, we can plug that in for here, because that's exactly what we have. Delta derivative, partial derivative with respect to x, vy, minus partial derivative with respect to y of vx. So we plug that in. What we get is then now our line integral is equal to the curl of v in the z direction. And now what we do for the integral is we start making our delta x and our delta y vanishingly small. And so the limit as s, our contour c encloses s, so we're just making this extremely, like the line integral, the actual curve, very small. That means the component here, the curl in the z direction, so the z component of the curl of z at a point is the line integral over here on a loop around a point divided by the area of the loop. That's this here. So the limit as the loop becomes vanishingly small. Thus, the curl does not directly tell us anything about the circulation on a macroscopic scale. In other words, the curl doesn't tell us anything about the circulation, about the bigger travels in curves or circles. It's talking about things at a much smaller level, the rotations. And that was our last topic. So that's it for this video. Thank you for watching.